Good afternoon, everyone, in Taiwan and also in Japan and somewhere else. Today, we are very happy to have Professor Youshifumi Saito of JAXA to give us a talk on the space plasma instrument. And Professor Saito was newly elected the AOGS Fellow, and maybe I would read his citation to introduce him. It says that Youshifumi Saito is a professor at the Department of Solar System Sciences, Institute of Space and Astronautical Science, that means the ISAS, JAXA. He received his master's degree from Kyoto University in 1991 and his PhD from the University of Tokyo in 1995. His research activities have been related to sounding rocket and satellite experiments for study of space plasmas in the Earth's ionosphere, magnetosphere, and around airless bodies such as the Moon and Mercury. He has been participating in developments of the space-borne instruments for hot plasma and low-energy particle measurements. Based on the obtained data by the sounding rockets and satellite experiments, he has studied the elementary processes for transport and acceleration of charged particles in the space plasmas. He's a PI of MAP PACE on Japanese lunar orbiter Kaguya. And currently he's participating in NASA MMS mission as a co-I on the instrument FPI-DIS, and also on the ESA JAXA BB Colombo mission as a PI of the MPP experiment. And for ESA, the JUICE mission, Professor Saito is a project manager of the JUICE ISAS project. He's also participating in the LUPIS, which is a lunar polar exploration mission, by developing a neutral particle mass spectrometer to be installed on a lunar rover. So Saito-san is very busy since I know him 20 years ago. And he has, from a young scientist, has gone into a very, very pioneering and prominent space plasma scientist, senior scientist. And let's hear from him his experience in building the space plasma instrument. Please, Saito-san.
Okay, thank you very much. And thank you very much for inviting me to this seminar. And today I will talk about plasma particle measurements in space and our current activities on instrument development in our lab at ISAS JAXA. Okay, I will share my desktop. Okay. Okay. What we want to do is to understand the structure and dynamics of the terrestrial and planetary magnetospheres. And in order to do so, we are making in situ measurements of plasma particles, magnetic electric fields, and plasma waves by developing instruments on spacecraft and send the spacecraft to the place where we want to make measurements. And by satellites, we are making observation of the following parameters using instruments on spacecraft: a magnetic field and electric field, and thermal plasmas, that is below 10 eV, and low energy charged particles between 1 eV to 30 keV, and medium energy charged particles between 10 keV and 200 keV, and high energy charged particles higher than 50 keV, and neutral particles and plasma waves, and optical measurements, including UV, EUV, visible light, and so on. So my talk is mainly about low energy charged particles and high energy charged particles. And charged particle measurement is like this. Charged particle analyzers measure the current or number of the electrons or ions entering the analyzer. And the measurements are made with a fixed sampling time, discriminating the energy, direction, mass, and charge state of the charged particles. So we are developing instruments that can measure electrons or ions one by one. And this figure shows the energy range of the charged particle measurements. it is divided into 3 energy ranges: low energy and high energy and medium energy between them. That is from 1 eV to 100 mega electron volts. And I divided the energy range into these 3 parts because the measurement technique is different between these energy ranges. For low energy, we are using electrostatic analyzer, and for mass measurements, we use time of flight techniques, and for detectors, we are using MCP or channel tone. I will explain in detail later. And concerning the high energy particle measurements, we are using time of flight measurements and also using the SSD for detectors. And for medium energy range, we are using both techniques. Electrostatic analyzer and time of flight measurements, and SSD and MCP are used for detectors. And low energy range covers the atmospheric plasmas and lobe plasmas and solar wind plasma and plasma sheet plasmas. And high energy range covers the radiation belt particles. And by measuring medium energy range, we can investigate the acceleration mechanism of plasma sheet of low energy particles to high energy particles. Okay, so from now I will talk about the low energy particle instruments. These are called plasma analyzers. The energy range is between 1 eV to 30 keV. And these analyzers can be categorized into 2 instruments. One is energy spectrometer, and another is mass spectrometer. Energy spectrometer measures energy spectra of charged particles. Energy spectra is like this. The horizontal axis is energy, and the vertical axis is flux or count. And the instruments that can measure energy spectra is divided into 3 categories. One instrument uses electric field, and another instrument uses magnetic field, and some instruments uses solid state detector, that is the semiconductor detectors. And the instruments that uses electric field includes Faraday cap, or spherical deflectors, or cylindrical deflector, or electrostatic mirrors. And in my talk today, I will explain the spherical deflector mainly. And concerning the mass spectrometer, it measures energy or mass spectra of charged particles. And mass spectrum is like this. The horizontal axis is mass, and the vertical axis is flux or counts. And those mass spectrometers uses electric field plus magnetic field, or AC electric field, or energy measurement plus time of flight. And today's my talk. In today's my talk, I will explain the energy measurement and time of flight measurement instrument. Okay, and this figure shows the principle of electrostatic analyzer. And this is the simplest instrument. It consists of 2 metal plates, here and here, and applying a high voltage to the 2 plates. One is positive voltage, and another is negative voltage. And when positive ions come from the left-hand side and enter into this instrument, well, the ions feel the electric field between these 2 plates. And when the energy of the positive ion is very high, well, it is not affected by this electric field so much, and nearly fly straight and go this way. And if the incident positive ions has low energy, it is affected by the electric field, and the trajectory becomes like this and collides with the negative plates. And if the energy of the ions is good, appropriate, it flies like this and collides with the charged particle detector placed here. Okay, so this is the simplest shape of this electrostatic analyzer, and it is called electrostatic deflector. But we cannot use this simplest instrument in space, because usually this charged particle detector is also sensitive to the photons. So in space, we have a solar photons, and the amount of the solar photon is about 10 to the 12th per square centimeters per second around the Earth. So that number is significant. So we have to, reduce the number of the photons in space. In order to do so, we can use this type of instrument. This is called spherical deflector. And it is nested spheres like this, the outer sphere here and inner sphere here. And when positive ions go into this instrument from the left-hand side, if the energy is too high, it collides with the outer sphere. And if the energy is too low, it collides with the inner sphere. But if the energy is appropriate, it can go through these nested spheres and go into this charged particle detector here. And talking about the photons come from the sun, the photons are not affected by the electric field between these two spheres, so go straight on and collides with the sphere. And if the sphere is blackened, the photons are absorbed. So, well, this kind of instrument can be actually used in space. This photo shows one of the examples of the electrostatic spherical analyzers really used in space. And this is an instrument called LEP-EAI and EAE on geotail spacecraft. And you can see that there is a quarter of a sphere here. And looking at the cross-section of this instrument has this shape, and there is a nested sphere inside and outside. And inside nested sphere plates measures electrons, and outer spherical plates measures ions. And we are using detectors MCP and channel tone here in here. And the previous photos are taken from this side, indicated by this red arrows. And this instrument is called 90-degree spherical deflectors, or quadrispherical analyzer. And this instrument was on board geotail spacecraft that was launched in 1992, and its operation ended last year. Well, the right-hand side of this figure shows the orbit of this geotail spacecraft, and the left-hand side figure shows the geotail spacecraft in operation configuration. And this circle indicates the moon orbit. So the geotail spacecraft went into the, and the left-hand side is the sun. So this figure shows the orbit of geotail spacecraft 3 years after the launch. And during 3 years after the launch, it measures magnetotail. And after that, the orbit is lowered to the near perigee of 10 Earth radii and apogee of 30 Earth radii, and continued operation for 27 years there. Okay. And talking about the detectors, charged particle detectors, we are usually use channeled electron multiplier or microchannel plate for detecting electrons or ions. And in order to detect single charge, charged particle multiplier is used. And when electrons or ions enter into this channel tone, collides with the it is a tube, and in the tube wall, and there it emits the secondary electrons. And electric field is applied, the high voltage is applied this way, negative high voltage and positive high voltage. So the electric field is from the entrance to the exit. So generated secondary electrons is accelerated by this electric field inside the this tube, and the secondary electrons again collide with the wall of the tube and emits the secondary electrons. and secondary electrons are multiplied and exit from the edge of this device. And single particle is multiplied to about 10 to the 7th using this type of device. And the bottom figure shows the MCP microchannel plate. And this is the consists of multiple small tubes. And it is made of a kind of glass, lead glass. And the size is shown here. And when we apply high voltage between front side and back side, well, when the charged particle enter into this tube, they collide with the tube wall, and secondary electrons are emitted, and it is multiplied and exit about multiplied to about 10 to the 4th charged particles. Okay, so this can be used as a two-dimensional device, and channel tone is a one-dimensional device. Okay, and this photo shows an example of a channel electron multiplier. The size is shown here. This is from here to here is 5 centimeters, and you can see these tubes here. And this is very fragile, so it is difficult to install in an instrument. Okay, but these days we have another type of channel tone called ceramic channel tone, made in Germany, and that is the block of the ceramic, and some tube is graved inside. So those kind of ceramic channel tone is rather easier to use. Okay, and when we use the channel tone, we use this kind of charge amplifiers. Charge amplifier converts the charge cloud multiplied by this channel tone or microchannel plate, and it converts the charge to a voltage pulse, charge pulse to the voltage pulse, and using this feedback capacitor and feedback resistors. And the voltage pulse, the number of the voltage pulse is counted by a counter. So when the one charge, one electron or ion enters into this microchannel plate or channel electromultiplier, one voltage pulse is output from this charge amp, and the number of the charge pulse and the voltage pulse is counted. Okay. And talking about the 90-degree spherical deflector on the spacecraft, well, there is an incident area, particle inlet here, and when the particle fly from the in front of the this inlet, it flies like this way and detected by the detector in the center of this analyzer. And when the particle come into this instrument from a little bit different direction, it flies like this way and detected by another detector here. And when the particle incident from this direction 3, it flies like this and detected by this detector number 3. So by detecting the position of the output place of these incident particles, we can detect the direction of the incident particles. Okay, so in case of this 90-degree spherical deflectors, we'll install this instrument on the side of the spacecraft like this, on a spinning spacecraft. So by doing so, we can cover three-dimensional space utilizing the spacecraft spin motion. Okay, and this figure is looking at the spinning spacecraft from the spin axis direction and dividing into the spin plane into 16 sectors in this case. And we'll change the voltage applied to the analyzer for each sector in each sectors. And by doing so, we can measure the energy spectra of ions or electrons for 16 sectors in this spin plane. And this instrument has multiple channels in the polar directions. So using those data, we can obtain the three-dimensional energy spectra of ions or electrons. This is the case of the geotail spacecraft, and the spin period is 3 seconds. So in the geotail case, we could obtain the three-dimensional energy spectra every 3 seconds. And we usually use ET spectrograms for displaying particle data. The horizontal axis is the time, and vertical axis is the energy, and particle flux or count is shown by color map. And the left-hand side figure shows an example of ET spectrograms obtained by geotail spacecraft. The top 4 panels are for electrons, and the bottom 4 panels are for ions. And this is the data obtained when the geotail spacecraft crossed the plasma sheet lobe boundary in geomagnetotail. It was obtained in 1995, so it was about 30 years ago. But we can see that in the magnetotail, this is the anti-sunward direction ions. There are very cold ions here. That is the lobe cold ions flowing towards the magnetotail. And when the spacecraft entered into the plasma sheet, we observed the hot plasmas like this. And between the hot plasmas and the lobe cold ions, we have the region where 2 component ions are observed. One component is low energy ions are accelerated, and higher energy ions are decelerated like this. So this is the typical signatures of the ions in the plasma sheet lobe boundaries. Okay. And so far I talked about a 90-degree spherical deflector. But these days, the most of the energy analyzers to measure ions, electrons, low energy ions, electrons, are top hat type electrostatic analyzers. This is the shape like this, and this is the cut out the top of the outer sphere and place the hat. So this is called the top hat type electrostatic analyzer. And this is symmetrical to the center axis. And when charged particles enter this way, it feels the electric field inside and fly like this and detected by this detector here. And so by detecting the position of the output of the particles, we can decide the direction of the direction of the incident particles. Okay. So so we use the MCPs here to multiply the incident particles, and behind that we use the MCP anode like this. This is the metal plate here, and divided into the several parts. And by deciding the position of these output particles, we can decide the incident direction of these particles. And this is an example of the MCP anode using with the microchannel plate. And this is called the delay line circular one-dimensional position sensing anode. And okay, there is a zigzag pattern like this here for the 300 degrees from here to here. And at the edge of this zigzag pattern, we have a terminal A and terminal B. And when the multiplied charge hit this, for example, this position, the time when these charged particles travel from here to the terminal is different between this terminal A and terminal B. So by measuring the time difference of the detected pulse between terminal A and terminal B, we can decide the position of the particles here, like this. So by deciding the position, we can decide the incident direction of these particles. Okay. Next, I will show you an example of the top hat type electrostatic analyzer in space. This is an Arase spacecraft launched on 20th December 2016, about 7 years ago. And on this spacecraft, we have a LEP instrument. This is a typical top hat type electrostatic analyzer. And this instrument is developed by Kazama-san in Taiwan now. And this instrument has a top hat type electrostatic analyzer here. And it has a MCP assembly here, MCP and its MCP anode. And below that, this instrument has a preamplifier here. And below this, there is an FPGA board that is the electronics board to control this instrument. And this instrument also has a high voltage power supply board here, and also power supply unit here. Okay. And this figure shows the ET spectrograms observed by this instrument, Arase LPE, and we can see very beautiful ET spectrograms. And next example is an electrostatic analyzer on Bepi-Colombo MIO. Bepi-Colombo is a Mercury magnetospheric Mercury exploration spacecraft, and now it's on way to Mercury. And it was launched in October 2018, and it will arrive at Mercury in December 2025, so about 2 years from now. And this figure shows the Ariane 5 rocket in Kourou in French Guiana. The Bepi-Colombo spacecraft is on this Ariane 5 rocket. And the right-hand side figure shows the MIO spacecraft in ISAS-JAXA. And this figure shows the MIA, Mercury Ion Analyzer. That is a toroidal electrostatic analyzer with electrical sensitivity control, and it measures low energy ion spectra, energy spectra. And this is the photo of this instrument. And the cross-section of this instrument is shown here, and it has a top hat, basically it is a top hat type electrostatic analyzer. But there is, we can apply high voltage to this top cap also. And in Mercury, the solar wind ion flux is very high, and we also have to measure the low magnetospheric ion flux simultaneously. So the instrument has to have a wide dynamic range, as wide as 10 to the 7th. And the dynamic range of the detector MCP or channel tone is about 10 to the 4th. So we have to manage the dynamic range of 10 to the 3rd before entering the MCPs. So this instrument equipped with this function of electrical sensitivity control by applying high voltage to the top cap, and also it has mechanical attenuation grid in the some part of the incident area where solar wind ions will enters. So by doing so, we can manage the 10 to the 3rd dynamic range by using electric sensitivity control and mechanical attenuation grid. So totally, we have succeeded in implementing 10 to the 7th dynamic range in this instrument. And this instrument also uses the special anode, MCP anode, called ASIC anode, multi-anode with ASIC. And a very small ASIC chip is installed on backside of this anode. And this ASIC includes 64 channels, amplifiers, and counters. Okay. And I will next show you the example of the data obtained by this MIA instruments on Bepi-Colombo MIO. This is an example of Mercury flyby number 1. It was obtained on September 10th in 2021. September 3rd, between September 30th and October 2nd in 2021. And this is the orbit of the MIO spacecraft during Mercury flyby. And the closest approach was around here, about 200 kilometers altitude from Mercury surface. And this figure shows the ET spectrograms of ions, low energy ions obtained by MIA. The top panel is the ET spectrograms. And position of the bow shock or magnetopoles, or it's shown here by this red line. And the closest approach is shown by this dashed line here. And the horizontal axis is the time from here to here is 22 o'clock to 0:30, 22:30 to 0:30 on October 1st and October 2nd. And this orange box indicates the shadow period. And zooming into this part, including the closest approach, we have this ET spectrograms. From here to here is 5 minutes. And the vertical axis is the energy between 10 eV to 10 kV or 20 kV. And we can see that there is the ions has this spectrograms between 2330 to 2333 2 or 3. The only low energy particles ions are observed, and after that, hot high energy ions are observed, and between them we have a region where two components of ions are observed simultaneously. And comparing this ET spectrograms with the ET spectrograms observed in the Earth's magnetotail, we have the similar signature for ions like this. So the ET spectrograms obtained in Mercury during the Mercury flyby, this may show the similar region in the low plasma boundaries. Okay, but the difference is that this is only 5 minutes, and in case of the geotail case, this is from here to here is about 30 minutes. So in Mercury, the time, the temporal change is very fast. Okay, next I will show you the mass spectrometers. And okay, and this is an example of the mass spectrometer. That is the Arase LEPI instrument. And it measures energy and a spectrum and a mass spectrum, and it uses energy measurement plus time of flight measurement. And the cross-section of this instrument is shown on the right-hand side figure, and it consists of top hat type electrostatic analyzer here, and below that we have the mass analyzer part. And there is a very thin carbon foil here, and when the ion collides with this carbon foil, because this is very thin, it can go through this carbon foil and pass through this carbon foil, and ions are accelerated and collides with the MCP here. And when the ion passes through the carbon foil, secondary electrons are emitted, and the secondary electrons fly like this. And the flight time of the secondary electron is much faster than the ions. So we can measure the time difference between the secondary electron and the ions. So by doing so, we can measure the time of flight of these ions from here to here. So because we know the distance from here to here, we can calculate the velocity of these ions. Okay. And using the top hat type electrostatic analyzer, we can detect the energy per charge of the incident ions. And using this time of flight measurements, we can measure the velocity of the ions. And using both information, energy per charge and velocity, we can calculate the mass per charge. So this can function as the energy, this can determine the energy and mass of the incident ions. And this is an example of the ET spectrograms obtained by this ion mass spectrometer, Arase LEPI. And these two red box indicates the proton ET spectrograms and oxygen ET spectrograms of measured by LEPI. And next example is the Kaguya map-based IMA. This is also a mass spectrometer, but this is for planetary plasma exploration. And the cross-section is shown in the right-hand side figure. And it also has the spherical electrostatic analyzer. And because the Kaguya spacecraft is 3-axis stabilized spacecraft, it also has this part before the spherical analyzer. And by applying high voltage to these 2 electrodes, we can decide the direction of the ions coming into this instrument. And below the electrostatic analyzer, we have a mass analyzer part. And this is called the ADF mass analyzer, a time of flight mass analyzer. And the electric field proportional to the distance from the carbon foil here is applied to inside this instrument. And the ions pass through this carbon foil is reflected by the electric field and collides with the top of the instrument and emits the secondary electrons. And the ions, when passing through the carbon foil, it also emits the secondary electrons. And by measuring the timing of the secondary electron detection from here to here, and we can detect the timing that the ions are reflected and collides with that top part of this instrument. And from that information, we can determine the mass of this incident analyzer to this analyzer. So this is the example of the mass spectrometer for planetary exploration. And this is an example of the ET spectrograms obtained by this instrument. And we can decide the population or several populations of the ions around the moon. And the right-hand side figure shows the mass spectrum of this obtained by this instrument. And we can, the horizontal axis is the time of flight, and the vertical axis is the count. And time of flight corresponds with the mass of the incident ions. So we can see the peak of the potassiums or sodiums here and here. And other peaks are including the carbons or heliums and so on. Okay, so next I will briefly talk about high-energy particle detectors. This is the high-energy electron analyzer on board Arase, and it can measure the electrons between 70 keV and 2 MeVs. And it uses this kind of detector, SSD. This is called the solid-state detector. And the left-hand side figure shows the structure of this instrument. It uses multiple SSDs here, and there is an incident slit here. And in order to measure the energy of the incident high-energy particles, these SSDs are used. And when an electron interacts with the semiconductor detector, electron-hole pairs are generated. And the number of the electron-hole pairs depends on the energy loss in the detector. So we can measure the number of electron-hole pairs by measuring the charge output from this solid-state detector. And from this charge number, we can calculate the incident energy of the incident particles, because the we know the an electron-hole pair is generated by 3.6 eV energy. Okay. And so, and this is an example of the ET spectrograms observed by this high-energy particle instrument, and observed by Arase HEP instrument. And a similar kind of instrument is also on board Bepi-Colombo MEO spacecraft. And this is the HEP electron. This instrument measures the high-energy electrons. And this is the cross-section of this instrument. It is there is a pinhole here, and high-energy electrons enter into this instrument from here and collides with this directed by this solid-state detectors here and here. Okay. So it has the field of view of 11.4 degrees and 11.4 degrees divided into 5 directions. And this figure shows the example of the data obtained by HEP electron instrument. This is high energy electron data, and it is obtained during mercury flyby number 1. And the top line shows the electrons data below 190 keV. And when the closest approach to the mercury, the amount of the electron below 190 degrees decreases. And this is because the solid mercury blocked the high energy electrons, and the number of the electron decreased here. Okay. And on MEO spacecraft, we also have the ion instrument called HB ions. This is the photo of the HB ion instrument. And the cross-section of the instrument is shown here. And there is a thin carbon foil here. And high-energy particles enter from this direction. And when the high-energy ions collide with the carbon foil, it emits the secondary electrons. And because this carbon foil is thin, so incident ions pass through this carbon foil and collide with this solid-state detector here. And solid-state detector can determine the energy of the incident ions, as I explained before. And by measuring the timing of the secondary electrons here and the timing of the ions detected by solid-state detector, we can measure the velocity of the incident ions. And using this information, we can determine the mass of the ions. So this is also the mass spectrometer for high-energy ions. Okay, and using the rest of the time, I will introduce our current instruments development status at ISS JAXA. And as I explained, we have been developing energy mass spectrometer. And now our development direction is mass spectrometers for any destinations. And the first one is the energy mass spectrometer on board Kaguya, and it measured moon plasmas, launched in 2007. And after that, we developed energy mass spectrometer for a Colombo MEO, and it will measure mercury plasmas, and it was launched in 2018. And after that, we are now developing the advanced energy mass spectrometer for MMX spacecraft, that is a Phobos plasma, Phobos sample return mission, and it will measure a Phobos plasma environment at Mars. And after this, and we are also developing a neutral mass neutral mass particle spectrometer, and this is for LUBEX mission, that is Lunar Polar Exploration mission, and it will be installed on Moon rover and will be launched in 2025. And talking about the MMX mission, that is the Martian Moon's exploration, and now it is planned to be launched 2024, that is next year. And we are in phase D, and after the launch, the MMX will stay at Mars orbit for 3 years between 2025 and 2028, and observe the Phobos and Deimos. For Phobos from remote, and also in situ by landing on Phobos. And MMX will retrieve samples from Phobos in 2029. So this is the first sample return mission from the Martian satellites. And the main mission is the sample return, but we have a mass spectrometer, ion energy mass spectrometer on MMX. So that is MSA instrument. And the purpose of this mass spectrometer is detect the secondary ions emitted from the Phobos surface, for example, by solar wind sputtering or solar photon stimulated desorption. And also, it will measure the escaping ions from Mars. So these are the purpose of this mass spectrometer. And this figure shows the cross-section of this MSA instrument. It has nearly the same structure as the mass spectrometer on Kaguya or mass spectrometer on MEO. And it has an electrostatic analyzer here. And because the MMX is also a 3-axis stabilized, it has the additional electrode here to select the incident direction of the ions. And also it has the mass analysis part here and a little bit larger than the Kaguya mass analyzer part. So this instrument has nearly 100, more than 100, higher than 100 mass resolution. So it is very high mass resolution. Okay. And talking about the Lunar Polar Exploration Mission, LUPEX, it is the JAXA-ISRO collaborative mission. And JAXA is now working with ISRO to plan an international collaboration mission to obtain the data on the quantity and forms of the water resources present on the moon. And in order to determine the feasibility of utilizing such resources for sustainable space exploration activities in the future. And this is the moon rover of the LUPEX mission. And what I want to do using the this neutral mass spectrometer on LUPEX rover, well, this figure shows the moon-originating heavy ions measured by map pace on Kaguya. And these two columns shows the ion ET spectrograms, and this panel shows the ions, solar wind ions going into the moon. And this panel shows the ions originated from the moon. And you can, as you can see, these ions gradually increasing energy from the polar regions to the equatorial regions. And the zooming into this part, we have this panel here. And these ions indicated by this white box is the moon originating heavy ions. And looking at the mass spectrum of these heavy ions, we can see the peaks of potassiums here and sodiums here, and also peaks of carbon and oxygen here. And sometimes we have the peak at mass 18, and this may be waters from the moon. So we are going to investigate these peaks in the future. And so what I want to do using the neutral mass spectrometer on moon rover is that I would like to understand the destination of solar wind protons and the source of moon originating ions that Kaguya map pace observed at 100 kilometer altitude around the moon. And water in an icy state is expected to exist in the permanent shadow region inside the lunar polar craters. And hydrogen is supplied to the lunar surface by the solar wind, which combines with oxygen atoms in lunar soil to form hydroxyl groups, OH, or water molecules, H2O. And water molecules are supplied from also outside by micrometeorites. And those generally created H2O are transported to polar regions and captured in regions of low temperatures. So the origin and transport of these water molecules are my interest. And this figure shows the craters in the polar regions. And solar wind protons may directly enter into the craters in the polar region. So by measuring the water on the surface of the polar crater region, we can distinguish if these are coming from the solar wind directly or are transported from the some other places. Okay, so now we are developing the neutral mass spectrometer. That is a part of the REIWA instrument. REIWA is the Resource Investigation Water Analyzer. It consists of LTGA, Lunar Thermogravimeter Analyzer, and a heater part here. And the vaporized water is induced into our mass spectrometer and measures the mass spectrum. And this figure shows the name of the mass spectrometer is Triton, triple reflection reflectron, and the structure is shown here. And this figure shows the principle of this Triton instrument. When an ion source ionizes the incident neutral particles, and neutralized and ionized particles enter into this analyzer. And by applying pulsed high voltage to this electrode, the ions start flying inside this instrument and reflected for 3 times and detected by this MCP detector. And measuring the time between the starting of the ion start of the flight time and the detection time, we can determine the mass of these particles. Okay, and this instrument has 3 operation modes: triple reflection mode and single reflection mode. And the triple reflection mode has higher time resolution, but lower detection efficiency. And single reflection mode has higher detection efficiency, but lower mass resolution. So this figure shows the mass spectrum of the carbon dioxide observed by this instrument. And top panel shows the triple mode mass spectrum, and the bottom panel shows the single mode mass spectrum. And the triple mode has the mass resolution larger than 200, and single mode has mass resolution about 65 so. And the this count is obtained by 1 minute data accumulation. So we can see that the single mode has higher sensitivity like this. Okay, so this is the my summary figure, a summary of my today's talk. And I talked about the magnetosphere observation by satellites, and I explained the low energy particle analyzers. For example, the example is the electrostatic analyzer, quadraspherical analyzer, and top hat type electrostatic analyzer. And I also talked about the charge part detector, channel tone, and MCP anodes. And I showed the examples of ion energy mass spectrometer. It uses the top hat type electrostatic analyzer and time of flight and relative time of flight. And I also showed the examples of high energy particle detectors. It uses the SST and time of flight measurements. And I also showed what we are developing now, that is the energy mass spectrometer on MEMX and neutral mass spectrometer on the BEX moon rover. Okay, thank you very much.
Yeah, thank you so much, Sato-san. I think this is a very detailed and comprehensive description of the technique you have developed. And questions are from the audience first. You could either just open your mic and ask questions or raise your hand. But let me ask the question first. The neutral mass spectrometer, you're mainly trying to measure the exospheric neutrals, right?
Well, in this case, I cannot measure the exospheric particles. This only measures the vaporized
I see. So you have the sample, right? And you have the pyrosis.
Right. Yes.
And then the question is, how long would be the length of operating? Will it be for many lunations or?
Well, this is I think this rover cannot survive the moon night, so it is operated only a half month.
So you have to be very quick.
Yes, that's right.
Yeah. Okay, that's very interesting. So it depends also where you land. That you grab some sample and heat it up. And then you say you have the triple reflection is because limitation of space, or I mean, you could have a more than triple reflection, right?
No, in this case, we have only up to 3 reflections. We can select only single reflection or triple reflection. Yes.
Why is there only triple? I mean, you cannot do it more?
Well, one of the reasons that we'll design like this is that the single mode can be used for redundancy, because this pulse high voltage we are using here and here is a newly developed equipment. So even one of the pulse high voltage fails, well, we can use this instrument using the single mode. And another reason is that by changing the pulse timing applied to this this electrode and this electrodes, we can select the mass range of this incident detecting particles. So well, I designed like this time. And for the main purpose of this instrument is detect the water, and we don't need such high mass resolution. Well, up to 200 is enough.
Yeah, but from the Apollo mass spectrometer experiment, they also found, I think, methane
Yeah.
So you should also be able to see me playing also this mass 16, right?
Yeah. So we can measure the such kind of molecules also. For example, this is the mass spectrum of the carbon dioxide. Mass number is 44. And so we can measure the methane. If there is methane, that will be around here.
Or I can read it to you. It's ask why a Lamia probe will not be used in lupus mission to measure the near surface plasma.
Okay. Well, for Lupix mission, ESA will provide another mass spectrometer for exospheric particle measurements. And talking about the very low energy plasmas, we may need the Langmuir probes, but I think the density of the around the moon is very low to use the Langmuir probes. Maybe much too low.
This question is from Chinish, right, Sana? And from a physical research lab. I think PRS involved in this mission, lupus.
Who?
You can see the Chinish Sana. Must be a scientist at the physical research lab in Ahmedabad.
Yes, good afternoon. I am a PhD student in Physical Research Laboratory, Ahmedabad.
Okay.
So actually, you have also known that the Chandrayaan-3 also have a Langmuir probe called Rambha, and they have measured some near-surface plasma measurements.
Okay.
So similarly, for the LUPEX mission, the plasma environment near the permanently shadowed region is very complex and interesting. Like to measure the electron density like that for this case, why we are not actually using the Langmuir probe.
Okay. You are talking about the lunar ionosphere, is that right?
No, not lunar ionosphere. The near surface plasma sheath, which has been developed due to the interaction of the solar wind and photoelectron emission.
Yeah. Okay.
To measure that, we need the Langmuir probe, right?
Okay, maybe yes.
So you have to convince your director to put the Langmuir probe on the lander.
Yes, like for Chandrayaan-3, there is one Langmuir probe 1 meter from the surface, and that gave some interesting result.
Okay, so how much is the density over there?
The density is very low. Like the initial result shows that it may have 30 electron per cc, and it may go up to maximum 200 per cc. It's very low.
Very low. So I think it is very hard to measure using Langmuir probes also. Is that right?
Yes, because the data which they have get is very dynamic, and it is changing for in a single hour. It is rapidly varying.
Okay, yeah, that's interesting.
Okay, good. Other questions from the audience? This is a very good and interesting question, and very relevant too for the lander experiment. So therefore, the lupus lander would only operate for half a lunation, which is a 2 weeks time.
Yeah.
I think that's perhaps the fate of the.
Actually speaking, because it is land on the polar region, the real night is only only 4 or 5 days, I guess. So there is some possibility that we can survive, but well, it is not a guaranteed yet.
It's a very daring experiment mission. Good. Any other question from the audience? And of course, the transport from the pole. Across the permanent shadow region is a critical problem, in the whole business of water transport. So I think this is very, very important experiment.
Okay. Yeah.
And also, if you also have a CO2 mass, you also measuring CO2. And I think that the Chandrayaan-1, this impact probe also measures CO2.
Yeah.
Yeah. Right.
Yes.
So that's also very interesting.
So yes, so CO2 is carbon dioxide is one of our targets. Yes.
Yeah, well, where do they come from? And it definitely could not be from the solar wind.
But it comes from the micrometeorite or something like that, or it may be well, originally it was included in the moon itself in the beginning, from the formation of the moon. Well, one of the example of the Kaguya spacecraft, we observed carbons from the moon.
Right.
And the amount of the carbon is larger than the we expected, calculated incident carbons from outside. So that is one of the results of Kaguya.
Yeah, I think one of the important results from Kaguya, I mean, I remember it's a paper by Yokota-san, right?
Yes.
Yeah, yeah. And but that is still with some uncertainty.
Yeah, right. Yes.
But it's make a very good case. Yeah.
Yeah.
Okay, great. Saito-san, if there's no more questions, we will let you go. And as I said earlier, we would arrange to organize your visit to Taiwan.
Okay.
In early next year.
Okay, thank you.
Okay, good. Thank you everybody for coming to this meeting. For this session. It's very interesting for me. And I think the video will be put on the webpage and also on YouTube for people to take a look. I think it's very, very, very important source, for plasma instrumentation. We're happy to have a whole almost an hour of lecture by Saito-san. Usually he just speaks for 15 minutes, Yeah, you have so I think that thank you so much, Saito-san, for a very, very, very beautiful lecture.
Thank you very much for giving me this precious opportunity. Thank you.
Thank you. See you then. Bye-bye.
See you. Bye.